Hi students, welcome to my lectures on mechanical unit operations. In this video, we are going to discuss about the different laws used for different crushing scenarios. As I explained in the last video, we have three different kind of crushers. One is for coarser crushing, second is intermediate, and third fine, and four ultra fine. There are different laws, empirical laws comes and applicable for different crushers. Okay, let us go for the different laws. These laws are empirical in nature. Okay, empirical means the laws which were framed mostly because of the experiments and experience. The laws which are framed mostly because of the experiments and experience, that comes under empirical laws. Let us go to the different laws proposed. Okay, later on we are going to solve an example. As you can see on the board, the first law that is proposed in 1867, which is a Rittinger's law. Okay, and every law comes with one formula, and every formula based on what is the controlling aspect. The controlling aspect for the Rittinger's law is work required. That means our ultimate agenda is to find out the work and power requirements, right? Let us define. The work required for size reduction is proportional to new surface area created. That means if I crush the material, and because of the product which is formed, which is a new surface, okay, and the law which takes more surface into consideration, that is law, the Rittinger's law. Work required for any size reduction is proportional to the new surface area that is created. This law, the Rittinger's law, is more useful for fine crushings. Fine crushing means when you talk about the sizes which are less than 0.05 mm, those comes under the fine crushings and ultra fine crushings, and the crushers which deals with this particle size less than 0.05 mm, that Rittinger's law is more applicable. For this particular law, the work required is nothing but power by mass flow rate, is nothing but Kr, which is a Rittinger's constant, into 1 by d bar Sp minus 1 by d bar Sf. This is the formula. What is P? P is power in kilowatts. Here units also play a very important role. I want you people to concentrate on units also. P is the power in kilowatts, M is the mass flow rate in tons per hour, d bar Sf isotermine diameter of the feed, and d bar Sp isotermine diameter of the product. So when you put up all these things and you get this formula, right? Similarly, the second law which is proposed in the year 1885, which is Kick's law. What is this law is based upon? The work required for size reduction is proportional to the logarithm of reduction ratio. That means if I start with 100 mm, my product is 50 mm. My reduction ratio is nothing but 100 divided by 50. That means feed divided by product size is called the reduction ratio. This ratio is more, let us go back. Work required for the size reduction is proportional to the logarithm of reduction ratio. And what is applicability? This law is more useful for coarser crushing. That means feed size should be greater than 50 mm. Whichever the particles we are dealing with which are greater than the 50 mm, that comes under the coarse crushing, and the Kick's law is applicable for coarse crushings. What is the reduction ratio? Is d bar Sf by d bar Sp. That means feed diameter divided by product diameter. Work required, same way, work required is a power by mass flow rate is equal to Kick's constant into reduction ratio, ln of reduction ratio. What is ln? Which is ln is nothing but ln of reduction ratio is nothing but ln of d bar Sf by d bar Sp. This is called the Kick's law. This law is more applicable for coarser crushing. Okay, and let us go to the next law. The third one is Bond's law. What is the Bond's law based upon? The work required for crushing or size reduction is proportional to the square root of surface to volume ratio of the product. Okay, this law based upon this principle. And where this law is applicable? This law is more useful for intermediate crushing. What is this intermediate crushing? When talk about the sizes of the particles between 0.05 mm to 50 mm, this comes under the intermediate crushings. Okay, and what is this definition? Work required is proportional to the square root of surface to volume ratio of the product, which is proportional to, when you apply the scarcity principle, which SB by VP is nothing but 6 by 5S into DSP, D bar SP, and which is if we, that means work required is inversely proportional to the diameter of the product. Okay, this is what the basis for the Bond's law. That means work required is P by m dot is equal to KB into 1 by square root of product diameter minus 1 by square root of the feed diameter. This is called the Bond's law. Sometimes people want to find out with Bond's constant with some different principle, which is called KB equal to 0.3162 Wi, where Wi is the work index of the material of the particle, because its special case comes with the Bond's law, where you can find out the KB, which is called Bond's constant, from the work index. What is the definition of work index? It is the gross energy requirement in kilowatt hour per ton. That means it talks about the energy in kilowatt hour per ton to reduce a particle to such a size that 80% of the product pass through 100 microns screen size. Don't worry about this definition, and at this moment keep it in mind. To find out KB, people use work index. This is the definition of the work index. Later on we will solve one example, thereby you can able to get more clarity. Let us apply these three principles, three laws, Rittinger's, Kick's, Bond's law, and later on we gonna find out what is the power requirements. Let us go find out what is the KB, what is Bond's constant, Kick's constant, Rittinger's constant. Okay. Dear students, I forgot to say, this Bond's law is proposed in the year 1952. It is more recent law compared to the Rittinger's and Kick's. Let us solve one problem on finding out Kick's constant, Rittinger's constant, Bond's constant, as well as the work index of the material by applying the three laws. What is the, let us go to the problem. The problem is calculate Rittinger's constant, Kick's constant, Bond constant for size reduction of a particle from a feed size of 50 into 10 power minus 4 meter to 10 into 10 power minus 4 meter. If the total power consumed is 40 kilowatts and the power consumed for empty run is 5 kilowatts, and given the mass flow rate of the feed is 20 tons per hour. Given this, we have to find out what is the Kick's constant, Rittinger's constant, Bond constant. Then let us go to the problem. What is the given? The P, load condition. That means when the machine is on, it requires machine to run its own as well as crushing the material. So that is what the given. P at load condition is 40 kilowatts, and P at no load condition, that is power consumed for empty run, is equal to 5 kilowatts. The difference between these two is the power gone into the crushing. That is what has to go into the formulas. And what is the mass flow rate? Which is 20 tons per hour. What is the feed diameter? 50 into 10 power minus 4 meter. And diameter of the product is 10 into 10 power minus 4 meter. And P is nothing but P load condition minus P no load condition. That is 40 minus 5. This is equal to 5 kilowatts. This is the Rittinger's law. Work required is nothing but power by mass flow rate is equal to Rittinger's constant into 1 by product diameter minus 1 by feed diameter. From this equation, I get Kr is equal to P by m dot divided by 1 by d bar sp minus 1 by d bar sf. I require majority of the students mistake in the constants. So follow this procedure. Always mention the units on the formula. What is the power? Is in kilowatts. What is the mass flow rate? Which is in tons per hour. What is the diameters will be represented given in meters. So put up all those units here because it will be very helpful. What is the P? Is a 40 minus 5, it is 35 here, and the 35 divided by 20, and what is the diameter of the product? 10 into 10 power minus 4 minus feed is 50 into 10 power minus 4. If you calculate, you get the Rittinger's constant value 2.187 into 10 power minus 3. Here it is important. Kilowatt hour into meter by ton. This is very important. Why? Because I have taken diameters in the meter, power is in kilowatts, mass flow rate is in tons per hour. So automatically, if you shuffle these units, you get Rittinger's constant is kilowatt hour into meter by ton. Similarly, you have to find out Kick's constant. The formula for the Kick's constant is WR, which is P by m dot, which is Kk, which is ln of reduction ratio, which is d bar sf by d bar sb. From this, what is the Kick's constant is nothing but P by m dot divided by ln of this. And what is the P? In kilowatts, m tons per hour. What is ln of feed by product? There is no units for the ln. So if you put up the respective constant, what is P? P load minus 40 minus 5, which is 35, divided by mass flow rate, which is 20, and ln of feed diameter divided by product diameter, you get 1.087 kilowatt hour per ton. Okay, here you got the meter, here you don't have anything because the meter got cancels out here. Similarly, apply the Bond's law, and work required is P by m dot Kb into 1 by square root of product diameter minus 1 by square root of the feed diameter. And what is the P by what is the Kb? P by m dot divided by 1 by square root product minus 1 by square root of the feed. And P is in kilowatts, m is in tons per hour, 1 by square root of diameter means 1 by meter power 1 by 2. So once you put up the numbers, if you calculate, you get 0.1. What is the unit here of the Bond's constant? Is kilowatt hour into a meter per 1 by 2, because it's a square root of the diameter, divided by ton. This is the Bond's constant. This is how you have to apply the formulas to find out the Bond's constant. Now let us go ahead to calculate the work index of the material. Okay, let us go ahead calculate the work index. Work index is used in the Bond's law. Okay, only requirement for the work index is make sure the units are consistent. Okay, as I have written on the board, what is work required is P by m dot is equal to what is the Bond constant. If you remember to the beginning of my lecture, it is called Kb is nothing but 0.3162 Wi. Wi is the work index of a material. 0.3162 Wi into 1 by square root of the product minus 1 by square root of the feed. See, the mentions follow the same units. Whenever you apply the Bond's law to calculate the work index, the unit should be the same. Power should be in kilowatts, mass flow rate is in tons per hour, and 0.3162, it's a kind of a constant, it has got a unit of mm per 1 by 2. Work index should be in kilowatt hour per ton, diameter should be in mm. Okay, if you wanted to use this formula to calculate the work index, the diameter you have to put it in mm, not in meters. Okay, because of this constant. Okay, the given numbers, if you same problem we are continuing. Therefore the work index is nothing but P by m dot divided by 0.3162 is nothing but 1 by square root of the product minus 1 by square root of the feed. Okay, diameter. P is 35 divided by 20. What is the work index? 3.3162 into 1 by 10 into 10 power minus 1. Earlier it was in the meter, 10 into 10 power minus 4. Okay, we have to convert in mm to find out this work index. So 1 by square root of 10 into 10 power minus 1 minus 1 by square root of 50 into 10 power minus 1. If you apply this formula, you get the work index of the material is 10 kilowatt hour per ton. Okay, it is very important for the gate related aspects also, and most of the people confuses in the applying the Bond's law through work index. Always whenever you use the 0.3162 Wi, remember always you have to use diameter should be in mm. Okay, this is a kilowatt, this is tons per hour, this is this is mm per 1 by 2, and you apply this, you will never do a mistake. Okay, thank you very much. Let us wait for my next lecture.